Hi, my name is Michael de Podesta, that's me, and this is a preview, if you like, of a talk that Andrea Sella and myself are going to be giving at the Cheltenham Science Festival on Wednesday, the 7th of June 2023. It's called Heat Pumps for a Cooler Future. Let me run through it. Here we go. So here are Andrea and I outside our homes. You see Andrea's beautiful heat pump there, his solar panels. This is my well-insulated home. And where are these homes? Well, they're here. Both of us have beautiful homes on this beautiful planet, but this planet has a problem. And this is the problem. It's not the only problem, but it's an important one. It's that we're putting carbon dioxide into the atmosphere. So this graph runs from 1700 through to just about 2020 and shows yearly emissions of carbon dioxide in billions of tons. And roughly speaking, we're putting about 36 billion tons of carbon dioxide into the atmosphere every year. Now, there are 8 billion people on Earth, so you see that's about 4 tons per person. And in fact, in the richer countries, it's many more tons than that. And that's part of the problem. We have no consciousness of emitting 4 tons of anything at all, and yet we are. So what's the effect of this? Well, if you look at the concentration in the atmosphere, this is the concentration in parts per million, and this is the same 1700 up to the present day. The historical concentration was 280 parts per million and stable, and now we're up at 420 parts per million and increasing at 2.5 parts per million per year, a 50% increase. And that's having a sustained and dramatic effect on the temperature of the Earth. So here is the global temperature anomaly. That's the difference in the Earth's surface temperature from this period from about 1850 to 1900. So you see here we're about 0. And since then, you can see the temperature is rising. Each blue dot represents an estimate based on all the meteorological measurements available on Earth at the time. And there are uncertainty in that in the grey bars. And then the red line shows the running average. And you can see here that it's increasing. So you can see that a lot of the increase has happened over my life and Andrea's life. So the climate that we're experiencing now is different from the ones that our fathers experienced or our grandfathers. And what worries us both is this: it's the climate that is going to be experienced by our children. We look to be set for very worrying temperature increases running into the future, caused by emissions of carbon dioxide. So this is the summary of the situation. The climate that we grew up in is gone. It's gone forever, and it can never, ever be retrieved. There's nothing we can do about that. Even if we emit 0 CO2, the Earth won't cool. That's it. However hot we make the Earth, that's basically what we have to then live with. But if we try very hard, we can stop it being worse than it might otherwise have been. And all we have to do is just stop emitting CO2. And that's what this talk is about using heat pumps as a way of heating our homes to stop emitting CO2. So how do we stop emitting CO2? Well, we emit CO2 from all these activities, but this talk is just about one thing. It's about emitting CO2 from heating our homes. It amounts to more than 30% of UK emissions. So it's a massive problem, and we need to solve it if we want to solve the whole problem of not emitting CO2 at all. So the problem arises because in a typical home, we use up a lot of gas each year, and each kilowatt hour of gas corresponds to very roughly 0.23 kilograms of CO2 emissions. You can argue in detail about this number. It's technical accountancy. It's somewhere close to that. So a gas boiler that uses up 12,000 kilowatt hours emits about 2,760 kilograms or 2.7 tons. So just living in our homes with a gas boiler, typically over a winter, we emit tons of CO2. It's almost inconceivable. The idea of a ton of a gas is almost inconceivable. The idea that we can emit 2 and a bit tons of something from our house and have no consciousness of it is astounding. That's part of the problem. But here is part of the solution. So 2.7 tons. But look, if we use heat pumps to heat our homes, we immediately deliver the same heating but reduce carbon dioxide emissions by 70%. And if we power that heat pump with renewable energy, we can heat our homes completely renewably. Wow, that's the big impact that heating our homes can have. So that 30% of CO2 emissions could become practically zero. That's achievable. So what is a heat pump? What is the magic that does it? Well, it's a box. It looks like this, and it replaces a gas boiler, supplies hot water, and heats radiators. It's just like a boiler. What we're going to talk about are air source heat pumps. We just don't have time to talk about other types of heat pumps, but that's you'll get the idea, I hope. So what you do is you put electrical energy in and cold water in, and out comes hot water. Fantastic. So now heating with a heat pump is different from other types of heating with an electrical heater here. So they heat by energy conversion. So here we put in electrical energy, it converts it all to thermal energy, and it's 100% efficient. Electrical heating is always 100% efficient. Fantastic. Great. 100% is pretty good. A gas boiler is not quite so good. We put in chemical energy from the gas, methane, natural gas, and out comes heat. But we don't get all the heat. Some of it goes out the flue, and depending on the boiler type, you'll lose some fraction. 10, 15, 20% is typical for what you lose in a boiler. But heat pumps aren't like that. Now, you do already have a heat pump in your home if you have a refrigerator, because a refrigerator is an insulated box with a heat pump. Let me show you. So there's the insulated box, and here's the heat pump. And the way it works is you put in electrical energy, and the heat pump does its stuff, which we'll talk about in due course, and it removes heat from inside and moves it to outside. So when you take heat out of the box, it gets cold. So down in the freezer, it gets to -20. So that's pretty cold. Outside, the outside of the fridge typically warms up to about 30 degrees Celsius. So to make this a way of heating your house, what you have to do is change where you put the insulation. So instead of putting the insulation on the cold end, you put it on the hot end, and you take away the insulation from the cold end. And then this is your home. So you see the heat pump stays the same. It's doing the same thing. You just change your focus on which bit you're concentrating on. Now it's taking heat from the outside, making it even colder, and putting it inside. So what we're going to do now is take a look at some demos of a fridge. Now, in the talk in Cheltenham, we'll do that live, but in this, we're going to split to a video cutaway thing. So here we are on location with a mini fridge. It's a little fridge here, and inside I can feel it just getting cold. And what you may not appreciate is that out at the back here it gets warm. And so what we're going to do is take a look at this fridge. We're going to switch to a thermal imaging camera. Take a look. Now you can see that the back of the fridge really is getting quite hot. And the inside, let's take a look at the inside. You can see that's got a really cold patch at the back, which is where the cooling takes place. So here's the mini fridge, and here's the house that we put in the way of it. And now you can see the hot bit is inside the house. And the cold bit here, we don't want it just to cool down a little bit. We put a fan here so that we blow air, and the heat pump in the mini fridge can extract the heat from lots and lots of air. And so when we switch to the thermal view, you should be able to see the house getting nice and warm. Here's the house. Something like that. And you can see that the heating is warming the house. Let's get it properly inside. And you can see the heating is warming the house. Now what we want to do to get lots of heat out of the environment is to get lots of air going past the inside. So we want to put a fan here so that we're blowing air. Here's the fan, and it's blowing air from my kitchen into the cold part, and the cold part extracts the heat energy from the air and puts it into our house. And that's how you get that's how an air source heat pump. Here we are back from the fridge demo. I hope you enjoyed that. So here's the heat pump again, and heat pumps move heat. And now you can see the key thing about heat pumps. If we put in 1 kilowatt hour of electricity, we're able to move typically 2 kilowatt hours of heat. And we move them, and both these sources go together, and out comes 3 kilowatt hours of heat. So that you're getting 3 kilowatt hours of heat out from 1 kilowatt hour of electricity. And this energy is scavenged from outside, harvested, if you like, from the environment. So that's absolutely fantastic. This efficiency is called the COP, the coefficient of performance. And very typically, it's 300% efficient. And this 300% efficiency is absolutely essential for decarbonising the UK's heating. Let me explain. Let's imagine a future where we have sufficient renewable energy that we're running all the heating in the country with heat pumps, and everything is wonderful. Now let's suppose that we said we don't want to use heat pumps, we want to use direct electrical heating. Remember, that's 100% efficient, whereas this is 300% efficient. What that is saying is we want a system where we have 3 times the amount of wind farms, 3 times the amount of solar farms, and 3 times the amount of nuclear. All this extra resource would have to be built, and that will take extra time, extra money, and of course we all pay for all that in the end. So heat pumps offer an incredible bargain, rapid route to decarbonisation. And if you're a fan of using hydrogen for home heating, then what you would have to do, that's even more inefficient than using electricity. So you would have to use 6 times the amount of renewable resource, 6 times the number of nuclear power stations, 6 times the number of wind farms and solar farms. So it would be this massive capital investment that would take decades to bring online, and cost vast amounts. So using heat pumps to decarbonise heating in the UK is absolutely essential to getting it done quickly and as cheaply as possible. So how do heat pumps work? How do we make heat move from cold to hot? Well, let's think about an analogy. And if Andrea were here, we'd say, Michael, analogies, they're all wrong, but some are useful. And here, this is another one which is kind of wrong, but kind of useful. So water naturally flows downhill all the time. So if we sort of lift up a little sluice gate here, we can see water will pour out from here. There it goes. Water pours out, and then the level goes down in the reservoir there, and it runs out. There we go. Water naturally flows downhill from high to low. but we can think of devices that make water move uphill from low to high. And so Andrea heard about these ancient devices from Syria, I believe. They're called Nuria. And so I managed to animate one in a PowerPoint. So this is a device, and if you put in work now, you can make this thing turn and it will dip below the water, and now water will naturally flow into it, and then you can lift it up, and now it's come high. So we've done extra work lifting up the water, but we've managed to make it go uphill. So water can flow uphill with a pump, but we have to do something to make it happen. So let's have a little cutaway for a demo of that. It's always lovely to come and play with water on a sunny day. So the question is, how do we get water to go from down here to up here? Because water doesn't naturally flow uphill. So what we do is we get a jug and we capture some of the water. But in order to capture it, we've got to put it below the level of the water. So it goes below the level of water and the water naturally flows into it. Then we have to do the thing that pumps do, which is we have to lift it up. We have to do work to raise it against gravity. And then to get it into here, we have to get it above the level of the water and pour it out. So there were two natural flows of water. One at the lower level, the water naturally flowed in. When we put the jug below the level of the water, then we do the work. And then the second one is it naturally flows out. And that's like what happens to heat in a heat pump. Okay, well, I hope you enjoyed that demo. It's kind of pointless, but it's always fun playing with water. So let's take a look at the equivalent thing now for heat. Here we've got a cold substance. So that's some cold substance is one where the atoms and molecules are moving rather slowly. And heat naturally flows from a hot substance where atoms and molecules are moving quickly to a cold substance, because when a fast molecule hits a cold molecule, the slow one speeds up, the cold one gets hot, and the hot one cools down, as in the fast molecule slows down. So let's bring a hot substance to sit next to this cold substance. And when they come next to each other, we get contact here, and heat begins to flow from the hot to the cold. So that's the molecular jiggling gets spread evenly throughout the whole thing. And eventually the heat flow dies away and we get left with an object at one uniform temperature. That's natural heat flow. But again, we can invent devices that move heat, as it were, uphill from cold to hot. So let me show you some of that. So if you have something cool and we bring in something really cold, so here's something really cold. So now when we put this here, the heat flows from the cool into the really cold, because the cool is hotter than the very cold thing. So heat flows in. So now we've captured some extra energy in that substance. Then we move it to a different place. And now we do the equivalent of the work that we did when we lifted the water uphill. We squeeze it, which, as it were, concentrates the energy of the molecules. And when you squeeze stuff, in general, it gets hot. We'll see that in a minute. And then when it gets hot in here, now that energy can flow out into this hotter place. So what we've done is come down here, we've captured some energy from here, brought it up here, and then released it in a hotter place. So that's the analogy. So let's see how that works in a heat pump. So heat pump, most of the practical ones for heating houses and the ones in refrigerators are basically a pipe, a single pipe, and inside it is a working fluid. And the working fluid, sometimes called a refrigerant, is a substance that has a very low vapor pressure. Sometimes they're a gas at atmospheric pressure, and you have to pressurize them to get them to be a liquid. And the pump has got a pump in it that compresses this working fluid. And so we apply electricity to it, and that starts going around. And that does two things. It moves the fluid around. Remember, to move heat uphill, we need to move it from the cold place to the hot place. And also it compresses it. Now, here, what we have is a flow constriction. So it's a very, very narrow piece of tube. It's called an expansion valve typically. and it's sometimes symbolized like that. So now you can see in this half we're compressing it, and then it reaches here and it can't flow easily through here, so this side gets to be high pressure, and then this side gets to be low pressure. So this one, and because we're compressing it, gets hot and high pressure, and this side gets cold and low pressure. So let's replace that, these words, with some colors. So just remember, red is hot, blue is cold. And now we can just move away and take a look at pressurizing things and making them get hot, and then expanding them and making them cool down. So here's the demo for that. I'll see you on the other side of the demo. So here's the bottle. It's got a car tire valve embedded in the lid, and here's the bottle. It's got a little bit of methylated spirit at the bottom to give it some actual vapor, and that goes to a little pump here with which we can pressurize and depressurize. So here's pressurizing. And then you can't really see it's hot. I can feel it's hot with my fingers. And then if we just take this apart and let's twist it. Oh, I think can you see some of the condensation in there? That certainly got cold. It feels a little bit cold, not very cold. Okay, here we go. That's 1 atmosphere. Wow. Could you see it get hot? Wow. So let's release the pressure now. So I'm just going to take this off here, take the tape off holding the bottle. And release it. So, well, I can see a lot of condensation in there. What can you see? Oh yeah, you can see the temperature's really shot down. So that's pressurizing to warm the working fluid, and depressurizing to cool it. Whoa, that was fun. Okay, so let's move on. So here we are, we're back with the heat pump going round, and how to make this into a heat pump. Well, what we do is we make this bit a very, very long labyrinthine tube, and we blow air over it from outside the house. So this is now air from your garden typically. And at this point, we arrange for the working fluid to be very cold. It might typically be minus 20 degrees Celsius. So if the air is at 0 degrees Celsius, then when air at 0 flows over working fluid at minus 20, then the heat flows from the air into the working fluid. And so we're capturing heat from the environment. And then we compress it, and at this point it gets hot, and so we flow it through here, and then we can flow water from the house past the hot bit of the pipe here, and out comes hot water. So in this bit, the working fluid might be at 50 Celsius, the water at 40 Celsius, so heat flows from the working fluid into the water. So when you look at this, the working fluid is trapped going round and round, but the net effect is to take heat from the air and move it into the water. That's a heat pump. Absolutely brilliant idea. Now there's a really important trick which we discussed whether it's too much, but I think you can take it. It's to do with the heat exchangers here. And we're just going to look at one of them here. This is where the heat is exchanged between the outside air and the working fluid. This one is where it's exchanged between the working fluid and the water in your domestic plumbing circuit. If we just sent working fluid past along here and let it warm up, so we've got air at 0 Celsius, here's working fluid at -20, and if it warmed up, then you can see that temperature difference is not so big, so the rate of heat transfer would be not so big. And if it just warmed up as it went through, like a normal liquid would, then at the end of it, it would have warmed up all the way, and we'd have very poor heat transfer. And so if we flowed 1 kilogram per minute of working fluid, and I've assumed it's propane, through the heat exchanger, when we can extract heat at a rate of 500 watts. That's not bad. Remember that number, 500 watts. But actual heat pumps use a trick. What they do is we begin flowing again, and here it's -20, and then we absorb heat from the environment, but here it stays at -20, and -20 here. It doesn't warm up as it goes through, but it's still absorbing heat. How can you do that? Absorb heat from the environment without warming up? This is how you do it. You have a mixture of a liquid and a vapor, and as you run it through here, what happens is the heat is absorbed, and instead of raising the temperature, it turns liquid into vapor. And as you go through, you turn as much liquid as you can into vapor. Now you might think, well, that's a bit odd. That's a strange trick. But this is what happens every day in your kitchen. If you boil some water on a hob, you put in heat and it gets hotter and hotter and hotter. But when it reaches 100 degrees, it doesn't get any hotter. It just starts turning from liquid into vapor, steam. And so this is exactly the same process has been engineered. The fluids have been chosen such that this happens not at 100 degrees, but down at some nice low temperature, -20 or so. So that's the trick. And if you do that, if you evaporate 1 kilogram a minute of working fluid in the heat exchanger, you can extract heat at a rate of 7,000 watts. That's 14 times more than if you just allow it to warm up. So that's one of the big tricks. And this is one of the reasons this cycle here, the heat pump cycle, is called a vapor compression cycle. So we're just going to cut away so you can take a look at some of this heat absorption stuff with a thermal camera. So here's a can of butane. Butane is the working fluid that's used in lots and lots of domestic refrigerators. And what we're going to do is we're going to extract some and put it into a balloon. So at the minute, it's at about room temperature and it's at about 2 atmospheres of pressure. So we're going to expand it and put some in the balloon there. Have I caught any? Not much. Let's try again. I think we've caught some liquid in there, and I'm going to tie the balloon. And you should be able to see the balloon is inflating, particularly if I put my hand on it. Oh yeah, I can feel it getting bigger. So what's happening now is that the air in the room is cooling as it makes contact with this, and the heat is being transferred into the working fluid, the butane, and then that's evaporating, but it's staying at roughly the same temperature. Let's take a look with the thermal camera. So there you can see the balloon, and you can see the very cold temperatures at the bottom, or -11 or something degrees Celsius. I can put my hand on there, and whoa, I can feel it, the balloon getting bigger. And you can see my finger where I've changed the temperature of the balloon on there. But it still stays very cold because there's still a little bit of liquid in the bottom there. And now oh yeah, there it's going. It's getting bigger and bigger. So that's capturing thermal energy from the room and turning a liquid into a vapor. And then in the second stage, when it's compressed, which I can't really show you, you squeeze this, and if you can squeeze it back and condense it back to being a liquid, you can release latent heat and make it get hot. So let's just summarize all the stuff we said about how heat pumps work. We start out here we've expanded it, and here the working fluid is cold, much colder than the outside temperature. And then we evaporate it. So this heat exchange is called the evaporator. The working fluid evaporates, capturing thermal energy from the outside air. Remember, it's colder than the outside air at this point. And then we compress it, and we have, at this point, we have lots of vapor and a little bit of liquid, and then we compress it to get less vapor and more liquid. And as it condenses, that releases so-called latent heat. The working fluid is compressed, increasing its temperature. And then here, the working fluid condenses, releasing heat into the domestic water supply. So at the actual talk, we're going to pause for more questions at this point. But here, we're just going to plow on. This is about heat pumps in our homes. So the first bit's about the technology inside heat pumps, and we include it because it's very interesting, physics and chemistry and physical chemistry and engineering. The second bit is about how heat pumps work in our homes. So here are some installations that people have. And the first thing we want to say is about the difference between heat pumps and gas boilers. So a heat pump supplies exactly the same amount of heat to your home as a boiler does, and there's no problem with that at all. But in general, it doesn't supply it at the same rate as a boiler. Boilers are much more powerful. So this is a graph. It shows time in hours. So this is 4 hours. And this is the heating power of a gas boiler. You see, it might be on at 20 kilowatts, and then it'll warm up your home very quickly and switch off. And then it'll wait for the thermostat to go back down, and it'll switch back on again and go like this. And that, of course, it could stay on for longer and put up to 20 kilowatts of home power into your home, 20 kilowatts of heating power. That's massive, absolutely massive, because the actual average heating loss in a typical UK home is about 6 or 7 kilowatts. So it's more like this. So a heat pump here will just operate at the average heat loss for your house. And it's very hard to make a heat pump that's 20 kilowatts of input. That's a very big, expensive object. So there's a difference in the way heat pumps and gas boilers operate. So there's a rule of thumb. I made a video about it. You can look that up. And it is a rule of thumb. It's not exact, but very roughly, if you want to see what size heat pump you need, take your annual gas usage, assuming you use your gas sort of normally, you keep your house at a warm temperature over winter. So you can find that either from your meter or from your gas bills, typically about your tariff section. I think it must be compulsory because it seems to be on all the bills. The annual consumption is, so here it's 8,600, here it's 6,800. Divide by 2,900. So divide this by 2,900, that comes to be about 3 kilowatts or something like that. That's a rough estimate for the size of heat pump you would need. Now, you might think that difference in power is really makes it not look good for heat pumps, but you'd be surprised. So let's just take a look at the flow temperature of the water in a heat pump system. So here's 2 radiators, and this side we've got what happens with a gas boiler, and here's what happens with a heat pump. So with a gas boiler, you might put in water at 70 Celsius. It would flow through the radiator and then come out at about 65 Celsius. And heat would be radiated into the room and passed into the room by convection. And typically you might get 1,000 watts transferred into the room from the radiator. Now, if you have the same radiator and you heat it with a heat pump, in general, you would only heat it to about 50 Celsius. It would go through and it would come out about 5 Celsius colder. And again, you would transfer energy by radiation and convection into the room. But very roughly, you would only expect to get about 500 watts of heat going out into the room. So it might seem that the heat pump can't blast in the power like a boiler. And if you have the same radiators, it can't transfer as much power like a boiler. But things are not so bleak. So this is a graph which shows, again, well, this is actually 5 hours here. And this is the flow temperature here. So this is very typical of what a gas boiler would do. But you could lower the flow temperature and just keep it on for longer. And that would this blue curve would transfer the same amount of heat into your home as this curve. And this green curve, which is what you'd aim for with a heat pump, transfers just the same amount of heat into your home as the red or blue curves. They all transfer the same amount of heat into your home. So with a heat pump, you're delivering heat at a lower temperature, but all the time, constantly. I'll show you what that means in my house. So the big question everyone wants to know is, will it keep my home warm? Well, it keeps my home warm. Let me show you data from my home. This is data taken every 2 minutes through the month of January 2023. Perhaps you can still even remember that. We had some really cold weather this January, and it's got 3 temperatures, this graph. This is the temperature outside, it's about 10 Celsius. This is the internal temperature, I was targeting 20 Celsius, and this is the flow temperature in the radiators. And so if we go through the month, you can see that the outside temperature is going up and down each day. So this is 1 week, 7 days. And the inside, you can see the flow temperature in the radiators is being adjusted. And you can see it matches the, when the outside temperature goes down, the flow temperature goes up. But look what happens to the internal temperature. It doesn't vary by more than, it's a plus or minus a half a degree or so through the entire month. The house was perfectly comfortable the entire time. So let's just take a look at the cold snap and a mild period. So here's a mild period, and here the average outside temperature is about 9 Celsius, which is very typical for UK periods in a UK winter. And we had to extract heat from air at 9 Celsius. So the working fluid had to be cooled colder. The heat would then flow from the air into the working fluid. Then we'd squeeze it up, but we only squeezed it to get up to 33 Celsius. That's feels barely warm. But when applied constantly, it's enough to keep the house warm. And here, the average temperature was 0 Celsius. So now we are cooling, the working fluid was colder than 0. Heat flowed from air at 0 Celsius. And at one time here, you see the air temperature was -9, but was still flowing, the working fluid was still colder, and the heat was flowing from the air into the working fluid. And then we're compressing it. We have to compress it harder now, and we have to heat it up to about 40 Celsius on average. So 40 Celsius is beginning to feel warm. But operating continuously, that's enough to keep the house warm. Over this period here, the average COP was 3.9. Remember, COP is the same as efficiency. So 1 unit of electrical consumption resulted in 3.9 units of heat entering the house, 390% efficient. This region, because we have to squeeze the working fluid harder, we have to put in more work, so the COP was not so good. The COP was only 2.8 over this period. So it was only 280% efficient. Now, 280% efficient is fantastic. This was the coldest week of the year, and it's operating with an average efficiency of 280%. So does it keep my home warm? Yes, it keeps my home warm. Now you want to know what it all costs, and this is a very interesting question. So I'll tell you the numbers for my home. So the cost was very roughly £13,000. The government gave me a grant of £5,000, so I paid £8,000. Has it saved me a lot of money? Well, if I were doing normal things, it would have saved me a little bit of money, but not so much. So the average COP over the whole year was 3.5. Remember, it was 2.8 in the really cold weather and 3.9 in the mild weather. But gas is much cheaper than electricity. And so you can see the ratio here is about 3, but the pump is about 3.5 times more efficient than a gas boiler. So in the normal case here, the running costs with a heat pump are likely to be a bit lower. I don't know, 10, maybe 20% lower, but the capital cost is very high. But that is not what I paid. So I want to show you what I paid for electricity throughout the year up to May. So this is what I paid. So last year, the year 2022, I paid £398 for all my energy consumption for the whole house. You can see here, January 2022, it's £55. January 2023, it was £128, very expensive month for me. So December and January were very expensive. But what makes a difference here, why I paid so little, is that we have solar PV and a battery. So the solar energy provides 10% of the bill, even in December and January. Quite astounding. It feels like there's no light at all at that time of year. In the summer, of course, we're completely off grid. This is just the standing charge. And then in winter, you see even in November, there's modest heating requirement, but there's still some PV available. And we have a battery. So in the winter here, we buy electricity at night when it's cheap, and then use it during the day when it's expensive, and that reduces the cost dramatically. So we come to the summary bit of the talk, and the summary is this: that Andrea and I love heat pumps. We really love heat pumps. Why? Because they use science and engineering to allow us to heat our homes with the lowest possible emissions of carbon dioxide. And they are the fastest way to decarbonize heating in the UK. So they're going to be a feature of our lives in the future, and we want people to embrace this and move on as fast as we possibly can. So we come back to this graph that we had at the beginning, and I just want you to notice that this line, this dotted line here, is dotted. These things, this is what happens if we just keep doing what we're doing now. But we don't have to keep doing what we're doing now. We have a choice. And if we choose wisely, we can change this. We can make this come over here, and our children will not have to endure the worst of what they might have to endure otherwise. Okay, thank you very much. This is the end of the talk. Here's the summary. Heat pumps offer us warmer homes and a cooler future. And these are the contact details of me and Andrea. And if you can manage to get this QR code, you can download a copy of the talk, the slides for the talk. Thank you very much.